I love walking around. Good afternoon, everybody. My name is Francesco. Thanks a lot for your attention and time. And my personal thanks to Brian and all the organizers for the wonderful workshop. I'm silent in the back because my background is only partially aligned with what has been discussed so far. And it's really quite a pleasure to have a chance to show you some recent work. So I'll talk about three things. Let me start by giving you a bit of an introduction. So my group and I have worked on a number of problems in power systems, active power flow, coupled oscillators, reactive flow, current reduction. I do teaching related to the research I do, and my textbook is available on my website for free. I'm also trying this new self-published and print on demand. So, and all of this work that I'll talk about today, and also much of that has been, supported by DOE through a contract listed down there, so also led by Brian. I think he mentioned it earlier today. And the papers I'll talk about, so these slides will be available, I'm imagining, so these are all live links, you can find them easily. Much of it is the work of my postdoc, Sabir, and some of the new results on the Lyapunov functions are the work by Kevin. And then also Brian already talked about some of the results, and so but I mentioned the paper here that we have together with Saraj and others. So clearly the focus of the entire workshop is on low inertia power systems and all of this hybrid situation with all sorts of devices interconnected, and on how do you assess frequency and voltage stability. So the three things I'll talk about today is I'll have two case studies. I'll talk about Droop-Controlled inverters, and then I'll talk also about PLL grid following inverters. And before I do that, I'll talk about some theoretical ideas that I would like to offer for consideration. And I hope they may trigger some thoughts. And I am very sympathetic to the way Duncan, for example, talked about it earlier, and also it was present in Brian's talk and others, about the really high complexity of trying to handle very large a number of devices interconnected through maybe a dynamic network, and then trying to perform stability analysis there. So even yesterday in the presentation by Dr. Kropowski, one of the questions, I think, paraphrasing it, I was trying to write down the sentence, how do you have future systems function together when you're going to be interconnecting a very, very large number of devices? So, I don't know how to do that. It's a challenge. So, certainly you may want to develop some principles to verify scalability and correctness, maybe by design. Maybe even if you don't succeed at the math. So today I'll be showing you some math, and clearly I will not succeed in handling the more realistic and most complicated system. Perhaps by doing some analysis, you can simplify the simulation work that will follow, right? When you are investigating these very large dimensional parameter spaces, maybe want to have some guidelines to cut down on the complexity of having to do that. And maybe even if you cannot really, again, do the full math, some of the mathematical understanding may help you gain some insight into how the system works. So having said that, what are tools that one can try to use? And yesterday, at the end of the day, there aren't very many that I can think of that are really sufficiently powerful. The classic one, of course, is the design of Lyapunov functions and the design of sets in the dynamics of the system. There are forward invariants, so you start in a set, you prove that you remain in the set, and then you find some kind of an energy function that decreases. Very closely related to that is the talk yesterday by Aranya Chakraborty on passivity-based and Hamiltonian structure. So my group also worked on that. It's the idea that, of course, there's some Hamiltonian mechanics to these rotating machines, and maybe also to the dynamics of the interconnections. Maybe you can use that. And what I'll talk about today is something that is less commonly used to power systems, but it's also a structure that is widely studied, has been studied over a decade. So I'll show you some references later that are referred to as monotonicity and contractivity. So let me give you a primer of what I mean by that. And so monotone, that's the first red sentence. Monotone means that you just have a bunch of nodes, and if variables at one node are increased, then the effect on the variables at other nodes are positive, and they are also increased. So you lift the voltage at the node, and perhaps in a resistive circuit, the voltages everywhere, the trend they feel is one of being lifted. Contractive means for a system that is monotone, and I'll be more specific in a second, being contractive means that it's, just the fact that you're monotone, that does not ensure stability. You need one more condition. You need to ensure that the system is contracting. There's a couple of ways to do that. It has to do with the amplification of the system compared with the attenuation in some elements. Equivalently, it has to do, and I will show you some formulas, it has to do with ensuring that when you compose the cycle the gains of transfer functions and of dynamic elements along a cycle, the cycle gains are less than 1, are less than unity. Or alternatively, one quite direct way of checking for it for a monotone system would be to solve a linear program. So I'll talk about that. Let me just be a bit more specific. So here I have an illustration up there of what, how would you check these loop gains for a little circuit example there. So to be a bit more specific, if you consider a nonlinear dynamical system there, I'll call it monotone if its Jacobian has elements off the diagonal that are positive or 0, so non-negative. So the partial of the f with respect to I, with the partial of the ith component of f with respect to xj, it's either 0 or positive. And so that's a matrix that in linear algebra is referred to as a Metzler matrix when the off-diagonal entries are non-negative. So it's rather easy to check. You would perhaps perform that with a symbolic software or simply by observation of various values of the parameters in the system. And so there is a fully developed and fully understood theory for when the system is linear. So if you're doing, for example, small signal analysis, stability analysis, then you would linearize. And what would you get? You would get a system that is just linear, and the matrix would have the structure of having non-negative off-diagonal elements. And so in this case, it's known that your matrix is Hurwitz, so all the eigenvalues are on the left half plane, if and only if you can solve a linear program. So you need to look for a vector of positive coefficients, and when you multiply on the right the matrix by the vector, you get a vector that has negative entries. And so what's nice about this is that this is much lower complexity than having to compute eigenvalues. You just have to solve an LP in the dimension of the network. In some cases, if the matrix M is sparse, then you may even be able to do it in a distributed way. So then you really cut down quite drastically on the computation time. And alternatively, even though it's written in what appears to be a more cryptic way here, this has to do with ensuring that the cycle gains computed appropriately throughout the network are less than 1. And so there's some formulas on how you would compute these gains, what properties do they have to have, but ultimately that comes down to just checking the cycle gains for every cycle. Some cases you may be able to even identify which one is the cycle that leads to the instability. Perhaps that gives you some insight in how to fix the problem. And if any one of these conditions here, so whether f is the matrix M is Hurwitz, or you solve the LP, or you compute the gains, these two things are equivalent. If any of these conditions are satisfied, then you know that automatically, okay, you have Hurwitzness, so you're fine. You have small signal stability, and moreover, in fact, it's more than just stable. You have a number of other properties. There's some robustness properties under scaling of the parameters. There's robustness to time delays. There's a number of additional robustness property that a system of this kind has that a normal linear system would not have. And then you see what's nice about this theory. This is the linear one, and then I try to draw slides that were literally exactly the same. And if you have a nonlinear system and you compute the Jacobian for the nonlinear system, now you have, it turns out that the same set, very similar sets of conditions. Here I think I'm overselling it. This is actually apparently the same. There's more complexity because this Jacobian, of course, you have to satisfy those properties at every point x in the state space. And there's other ways of formulating that we're still developing. So there's a number of equivalent formulations, but at some level, the linear analysis carries through to the nonlinear case, which is quite remarkable, if you can ensure that the system has the right properties. And moreover, the nonlinear analysis provides you even with an interesting new global Lyapunov function, which I will use in a few slides in my case study. There's one thing that happens in these slides, that blue arrow was an if and only if earlier, so there's no loss in the linear case, but in nonlinear, of course, I'm afraid I do have some conservativeness, and that's clearly undesirable, but let me just keep going anyway. So here, it's one way of designing Lyapunov functions by using the property, the monotone and contracting property of the Jacobian. All right, so I think this is just a summary. You can do local asymptotic stability analysis, small gain. You have computationally efficient methods. You have one of these other additional stability properties is the stability properties of trajectories. So trajectories of the system tend to converge to one another. So that's also helpful when you're doing simulations. If you introduce errors in the simulations, they get naturally attenuated for systems that have these properties. And I'll show you how I can use that Lyapunov function in a few slides. And for those of you who get the slide and want to follow up, these are also some classical references. You see, this theory of monotone systems and contractiveness was used not long ago, inspired by biology and ecology, then more recently, and then more recently again in the context of traffic networks. And these are some very almost contemporary papers that have appeared, picked up in the community that deals with large-scale network systems. All right, so that was an attempt by me to try to provide a new set of mathematical tools that we could try to use looking at large-scale networks of inverters. And as I said at the beginning, I'm not claiming it's the end of all problems. It's an attempt. Under some assumptions and conditions, I'll be able to show you that it's relevant in 2 case studies. But of course, much more work needs to be done here, and I don't think it will all be mathematical. So I do think, of course, that in the end we will run realistic simulations. So let me talk to you about a little bit about Droop-Controlled inverters and see how I use all of this. So this is a completely standard setup that has been used in the literature. Standard notion of frequency Droop control, standard formulas for the power injections and electrical power flowing on lines, and then after some more or less elementary manipulation, you get the formula at the top up there, which tells you the rate of change of the angle, so the frequency of each node. The Droop coefficients is related to the power injection or normalized power injections, and then of course that's the formula relating to the flow of power proportional to the power angle. So B here is the incidence matrix of the graph. So that B transpose theta gives you simply the vector of theta I minus theta j, and then A is the matrix of maximum power transfer on a particular line, as you do with the inductances, and P, as I said, is the power injection. 3 are the Droop coefficients. And it turns out that if you compute the Jacobian of that right-hand side of that system, it does have the right property of having all of the entries being positive or 0. They're strictly positive on every branch of the network, provided of course that the cosine of the angle is positive. So provided that the power angles on each line are less than pi over 2, or an angle gamma here, which has to be itself less than or equal to pi over 2. So here I've drawn, just to give you an idea, what do the sets look like where these properties are satisfied. So if you take, for example, 3 angles, actually I think in this case is 4, and you look at pairwise differences between theta 1, theta 2, theta 2, theta 3, theta 3, theta 4, and you draw which sets of angles satisfy that set of pairwise inequality. In that space, you get a polygon or a polytope that describes the set of angles within the set of angles theta 1 through theta n that satisfy the pairwise angle constraint. And so they're going to be polygons. They're going to be polygons. We're going to be working inside these, or polytopes, pardon me. We're going to be working inside these polytopes. And okay, so what is my objective in trying to analyze the system? I would like to understand, as a function of the parameters of the system, power injections, admittances, and topologies, I would like to understand when do I have some transient stability properties, right? When can I ensure correct behavior? And I have here 3 correct behaviors that I would like to ensure. One is frequency synchronization. As time progresses, I would like the frequencies to converge to the, to all be equal to the frequency synchronization, 50 hertz in Europe and 60 here. I would like to ensure that there are no large frequency variations at each node for all time. So that's the frequency constraint. And I would like to ensure also that along each edge, each branch of the network, that my angle difference keeps satisfying that constraint, right? And in fact, when this is less than pi over 2, then I know for sure that I'm in that set where I know my system is monotone. So then I can apply my analysis. And so the theorems is very, very simple, and it's not much more than what I already showed to you earlier, which is to say that if I do know that the pairwise angular differences are less than pi over 2, then in fact I showed you earlier my Lyapunov function, as Lyapunov function, I can just take the infinity norm of the system dynamics. Infinity norm means you take the absolute value of each entry and you look at the largest of them all. And that's the formula for what the system dynamics is. And just a little bit of algebra shows that that same system dynamics, after you rewrite it, is just simply equal to the frequency deviation at each node. And so the infinity norm is the maximum frequency deviation. So all of that theory of monotone system provides you with the Lyapunov function, and what it is just the maximum frequency deviation. So that's quite nice because, again, if I were to know that I remain inside that set, my system dynamics is monotone and contracting, and the maximum frequency deviation is not increasing. In fact, it's exponentially decreasing to 0. So, so that's quite nice. I do have a nice Lyapunov function with a nice physical intuition, and it's actually related to one of the criteria that I wanted to ensure. So now, how do I, as I mentioned earlier, when you have a Lyapunov function, it's typical, well, if you're lucky, it's global, and if you are lucky, it is valid over a certain region, right? Over the certain region, everything behaves properly. So then the next thing you need to do is you need to ensure that the region is forward invariant, otherwise the trajectory escape, and then you haven't proved anything, right? You haven't established anything. So the classical way to do this is to look at the boundary of the set that you're interested in, right? You look at the Lyapunov function, you look at the lowest value of the Lyapunov function on the boundary, and you ensure that you start below that value. If you start below that value and the Lyapunov function is decreasing, you cannot cross the boundary. And you can make it even more sophisticated in the sense that you have to look at the subsets of the boundary, the pieces of the boundary, where not only the value of the Lyapunov function is, you don't want it to be higher, but you can also eliminate all of those points where the derivative of the vector field is going inside. If you know you're going inside, you don't have to worry about those points. So little details to ensure that, to come down to a theorem that says that if you start inside, if you were able to compute this minimum value of the Lyapunov function on the boundary, and you start inside that level set, then everything happens the way you would like it to happen. So frequency synchronization, frequency constraints, and angle constraints are all satisfied. So it's all about being able to evaluate the Lyapunov function on the boundary of the set that you're interested in. And the set I'm interested in is, of course, this pairwise angle being less than or equal than gamma. So this gamma here in that set. So now you go work with sets, and you want to look for the smallest value of the Lyapunov function over the boundary of a certain set. This optimization problem is not convex, but the contribution that we made here is to find a way of relaxing it and obtain a lower bound on it, which is computable. And the convex relaxation, this is a picture of it illustrating. I have a sinusoidal function, and I overfit it with the convex polygon. And so that's the extent of what I want to say, to basically tell you that by solving linear programs, we are able to ensure all of those three transient stability criteria. Now, this is just to illustrate to you what I've done. I've just calculated the largest set, which is not this one, it's even bigger, such that all of the curves of the vector field bring you inside. So we did 2 case studies just to kind of, play with it. So we took the IEEE RTR74 system. We scaled down all of the parameters of the power injection to something that would be more comparable to a Droop-Controlled, maybe residential type inverters. And we did some case studies. And what we did is we imagined that there would be either a single contingency or 2 contingency, and those lines, either 1 or 2 of those lines would disappear. And what we studied is, I wrote it up there on the right, so we imagine that we want to ensure certain parameters of safety, gamma and delta. This, let me remind you, this has to do with the pairwise angular differences I'm willing to tolerate and the pairwise frequency differences that I'm willing to tolerate. And basically, so we're imagining we are at an equilibrium, the nominal one for the test case, with everything scaled down by 1,000. There is a fault, one fault or 2 faults. Now we verify if a new equilibrium exists, perhaps if the network becomes disconnected or not. And then we calculate whether we are guaranteed to be in the region of attraction of the new equilibrium, right? Guaranteed to be in the region of attraction of the new equilibrium after 2 faults, 1 fault or 2 faults. So here, the score S, this is, my Lyapunov function, does it become smaller or larger? If it becomes smaller, so if that number S is less than 0, then it turns out that I'm guaranteed to be safe. And so everything plotted here, so here, why do I have a matrix? Well, I have a matrix because, of course, I am an n-2 contingency analysis. There are 2 lines that are failing. On the main diagonal, there's only 1 line that is failing, of course. The plot on the right is symmetric, so it's a symmetric matrix. The color scale There's a 0 at more or less a whitish color, and everything in light blue is a negative value of my score, which means that I'm guaranteed 100% to be within the my stable region. And then everything going up in color of red is telling me which pair of edges are more critical, all the way, of course, to the, so the black color corresponds to lines that if you cut them, the network becomes disconnected. So we can perform analysis like this quite quickly without having to do any numerics. And here's another little case study that we did. So because we know something about our Lyapunov function and we know how quickly it decreases to 0 and it has this nice interpretation of being the maximum frequency deviation, then we're able to do this kind of, very preliminary, as I said, unpublished work. So we're assuming here that we have a microgrid with inverters, each of which has a battery, and we would like to understand how to spec the battery, so how much energy is required to be stored by the battery in order to handle some contingencies, right? And so the very, very simplified scenario is there is no reserve, there's no headroom here, as we've been talking about. The PV operates at the power rating. There's a fault. The fault generates a frequency deviation, and then the battery provides the energy through the Droop-Controller, and essentially for an arbitrarily long period of time, although most likely everything will happen within a much shorter time. So this is a very, very simplified scenario. It's unpublished. It's just a case study that we prepared for this talk today. And so this new Lyapunov function, which is the maximum frequency deviation, you can integrate it over time, and that gives you an estimate, an upper bound on the amount of energy that the battery at each node I needs to have. And so you look at that upper bound, the numerator has the square root of n, being the network size. It has the Droop coefficient, so the more you, the higher Droop coefficient you have, of course, the more energy you're going to need. And then at the numerator, there is also the maximum frequency deviation, so that's proportional to the fault, right? The fault will generate that. And then at the denominator, the only term I'll mention is that lambda 2, and that is related to the network connectivity. So the more connected the network is, the higher the inductances and so on and so forth, as measured by, this is the second eigenvalue of the Laplacian. So for those of you who have had a chance to play with graph theory, you would recognize that symbol. Otherwise, for the other of you, that's related to the admittance matrix. And so we are able to do a number of little things, and hopefully of potential interest. So that was the case in which we were able to use this monotone theory with contracting systems in a nonlinear analysis. Let me quickly show you also what we did. We did a study which is, I think along the lines of what Duncan talked about earlier today, performing small signal analysis of a large number of PLL-based inverters. And what the previous work was with Kevin and Saber. This next one is also with Brian and Sairaj. And Victor. So this is a block diagram of a three-phase grid-following inverter. I'm not going to spend time discussing the PLL, power controller, current controller, PWM generator, LC filter, and so on and so forth. Let me just say that after appropriate writing, you obtain a nonlinear set of differential equations, x dot equal f of x plus g of x I naught being the output current, so of course it's interconnected to the network, and then there's of course the nominal powers coming from the left, C P star Q star. So what did we do here? So here, exactly like what was said by many of you before, we did, first of all, we did a study where we showed that you really cannot ignore the dynamics of the grid following inverters, and that if you do small signal stability analysis, you will see that you will lose feasibility. And so here we have a network, a line network of 30 inverters interconnected to a point of coupling. So they're grid tied, of course. Very simple. Everything is identical. There's some values for the parameters here, and the plot. The only thing the plot says is that as a function of the power injections, singular I should say, because it's the same for every generator. As a function of power injection, there is a threshold at which the power flow equations quit having a solution. And so if you just work off of the power flow equations, you would imagine that you can inject all the way to, I don't know, about 1,800. And instead, the blue line that describes, that's plotted vertically, right, describes the value of the eigenvalue with largest real part. And so this is the eigenvalue that will cross and become positive, and therefore create instability like it was discussed earlier today. And so, okay, so one needs to worry about this. And so then the other thing we did is we're looking at a system that has 15 variable per state, and there's n of them interconnected. I'm not even considering the dynamics on the lines at this moment in time. So it's 15n. So for n very large, this is going to be very hard to analyze. So we try to simplify the complexity of this analysis to be able to do something analytic. Of course, we can run simulations or compute eigenvalues up to some dimension. And so here, there's some assumptions on timescale separations of the time constants of the LC filter, the current controller, and the PLL. Essentially, what we're assuming is that the power controller is the slower element of the PLL. And when we do that, we are capable of, and I'm not providing it here, but we're capable of writing a condition that requires it's only a matrix of dimension 2n. You need to compute the eigenvalues of a 2n dimensional matrix. So we're able to, reduce the complexity by 1 order of magnitude. And then in the second step, if one is willing to make additional assumption that the network interconnected inverters is resistive, then in fact one can show that after a change of variable, you do indeed get a monotone system described by a matrix whose off-diagonal entries are non-negative. And so if you're willing to do both the timescale separation and assume the resistive network, you do get a system for which calculations are very, very simple and can be carried out for very large dimensional systems. Because now everything is going to be a solution of an LP, the dimension of which is just n. And you can even maybe do it in a distributed way, as I was hinting at. And so the intuition here, well, I've already covered the second half of the slide. The intuition here is that as you increase the output current at one PLL, voltages will drop somewhere else, and therefore currents will increase at the other neighbors. Okay, so to cut a long story short, I've shown to you, let me just skip the first part. I've shown to you some ideas on how to try to do large-scale analysis. As I said, you can either have methods of designing Lyapunov functions, or you can use passivity. And today I provided to you an example of different sets of tools. If your matrix happens to have non-negative off-diagonal entries, please give me a call. And I've shown you two case studies where that structure does indeed appear. And yeah, I think the future work is clear for me. Thank you all.
All right, we have time for a couple of questions.
I have too much math.
Well, I'll ask one. So you had this property of monotone systems for nonlinear systems, and you said it has to be true for every point in the state space. Did you mean every equilibrium point, or do you mean? No.
Unfortunately, that needs to hold true at every point. And so then you need to find a way of. So I had two formulations, one with a linear inequality. So then you would have to either sample, but I believe the other one with the gains is quite tractable. So one would compute gains at each cycle, each edge, and then perform the cycle test.
Yeah.
I just had a question. When you look at contingencies,
yeah.
So you start with the Lyapunov function, and then with the contingency, the system changes. So you compute different Lyapunov functions for all the possible systems.
The Lyapunov function is the maximum frequency deviation. So I am at an equilibrium. I have a certain frequency. Now there's a contingency. I compute the new equilibrium,
okay.
And from there I just compute the difference, and I look at the maximum pairwise difference. So it's quite, yeah. There's a nice physical intuition, I think.
Any other questions?
Thanks, Francesco. So just maybe a high-level question about kind of scaling up to or over, I don't know which direction it is, to thinking about like the next level of detail on converter modeling, higher fidelity converter models. Do you think that there's a sort of direction in the Lyapunov style approach, or what are the sort of roadblocks to sort of bringing it further into
I think
higher fidelity model?
Yeah, I kept thinking about it. We've been thinking about it for a while. I don't know how to cut the complexity. If you tell me you have 15n and n is 1,000,000, how do I do the calculations of the eigenvalues? I don't know. So we're gonna, I don't know, and also the real system, of course, is gonna be much more complicated. So of course there will be realistic simulations as much as possible, but you're exploring a very, very large dimensional parameter space. So maybe knowing that you need to focus your computational resources here instead of there would be useful. Yeah, I think aggregation is one strategy that Brian talked about earlier today. That is certainly true. Yeah. I think some smart combination of tools to cut down. You're completely right. Yeah.
All right. If there's no more questions, we'll thank Francesco again.
Thank you.